Is it long? 5 to 7 questions.
Okay, let's get started, please. Okay, so let's remember where we are. We would just introduced the idea of the inner product space, right? So you got your abstract vector space, and you want to have something on it like a dot product, right? So you've got inner product spaces, and today we're going to be talking about something called orthonormal sets. Orthonormal sets. Or really the purpose of this section is to talk about something called orthonormal bases. Okay. And the problem that this is going to help solve for us is the problem of how does one get the coordinate vector. How do you get the coordinate vector, right? So, somebody want to remind me what a coordinate vector is? What's a coordinate vector? Bill?
You express some vectors in linear combination.
Right. So you've got your abstract vector space. You have some basis, v1 to vn, right? And then you have some vector, right? And you want the coordinate vector with respect to that basis, right? So you want the coordinate vector of v with respect to the basis b, right? And that is a bunch of coefficients, c1 through cn, right? It's something in Euclidean space, right? And you remember that what these things give you is a way of rebuilding your vector from the basis vectors, right? If you know what the coordinate vector is, you can reconstruct your vector as right, c1 b1 plus c2 v2 plus cn bn. Right? It tells you, what you need to put together to get your vector back. Okay? And so that's not always easy to get. Right? If I give you a bunch of polynomials and I say these polynomials are a basis, and I give you another polynomial and I say give me the coordinate vector of that, well, you have to do a fair amount of work to find the coordinate vector. Right? It's not so straightforward. Right? Some of you have pointed this out. Like, how do you get the coordinate vector? Well, in Rn, it's actually easy to, if you're given an unknown vector, suppose somebody gives you an unknown vector and says, I'd like you to tell me what its components are, right? I want you to tell me what its entries are. Right, so you've got this vector, v is v1, v2, v3 to vn, but those are hidden somehow, right? You can't see what they are, and you want to have some way of getting those things. Well, one way would be to use the dot product. You could say, well, I'm going to take the dot product. Maybe I don't know what this vector is, but I have some machine that will take the dot product with any other vector I choose. Okay, so I'm going to use my machine and say, let's take the dot product with the standard basis, the first standard basis element, right? And that would give me v1, right? That would pick off v1, right? Because you'd be taking v1 to vn against 1, 0, 0, 0, 0, right? And so that would pick off your first entry. Right? That would give you v1, right? And if I took it against whatever entry, whatever standard basis element, then that would pick off that entry, right? Against e2, it would pick off v2, etc., etc. Right? So this would give me a way of picking off the entries, and you see this gives me that a way of reconstructing my vector. Right? It's going to be v1. v1 plus v2, v2 plus vn. Okay, so there's something that's good. There's something good about the standard basis? There's something good about the standard basis, and that's what we hope to replicate in the abstract case. Okay, so we want to do something like, we want to get something like the standard basis, but in the abstract inner product space. Because once we have it, then we can figure out the coefficients of the coordinate vector easily in this way. Okay, so here's the sort of obvious thing to do. We say, well, look, if we have V an inner product space, and suppose you have V1 to Vn, a bunch of non-zero vectors. If Vi and Vj are orthogonal whenever I is not equal to j, then we say, we call this set an orthogonal set. Yeah.
So I is not equal to j.
Yeah. Yeah. So what we're saying is that whenever you take two different guys, they're perpendicular to each other. Okay. We don't want the guy to be perpendicular to itself. In fact, it's impossible. Right? You can't be perpendicular to yourself unless you're zero. Right? But these are all non-zero. So if whenever you take two different vectors, they're perpendicular, we say that there is a perpendicular set, an orthogonal set. Yeah, I'll go.
Does that hold for any inner product space that we make, or does it have to be like the
any inner product space? So like you take an inner product space, you have a set in the inner product space, and if those guys are all pairwise orthogonal, we call that set an orthogonal set. Okay, so here's an example. Let V be the continuous functions negative pi. Okay, and let the inner product be 1 over pi times the integral from negative pi to pi of f times g. Okay, this is an inner product that we mentioned two periods ago. Right? You just integrate one function against the other. Right? We're throwing in this constant. You'll see why we throw in this constant later. We just want to make things a certain size. We want to make certain things 1. So we divide by pi. It doesn't change anything. Okay, then, in fact, it's a calculus exercise to see that the set 1 cosine x, sine x, cosine 2x, sine 2x, etc. is an orthogonal set. So if you just take the integral of any guy against another guy, any two elements of this set, you'll see that that you get 0. Okay. So we haven't done anything yet. We just said we create this thing called orthogonal sets, right? Just means that any two vectors in the set are perpendicular to each other. Okay.
It's for that exercise, like how do we know?
I don't necessarily have to.
How do you what?
How do you know it's like an orthogonal set?
So what would you have to do? You'd have to check that. You'd have to check that whenever you take anybody in the set, like say sine 5x and cosine 3x, you get 0. Okay, so you take the integral of sine 5x against cosine 3x, and then after some work, you would see that equals 0. So it's a calculus exercise. I'm not gonna do it. But you have to pick any pair of elements and integrate them against each other. Yeah.
So you have to do every possible combination.
Well, you'd have to. That would not be the way to do it. Right? You have to do it in general, right?
Yeah, that has to be an issue.
Yeah.
Is this like related to linear independence at all? Or is it-
So there's a nice property of orthogonal sets that, so we're going to call it a proposition. If the set is orthogonal, then the set is linearly independent. I should just give you an extra point for that, for asking that question. Yes, yes. If the set is orthogonal, then the set is going to be linearly independent. Okay, so think of what we need to show, right? We want to show that if some linear combination of these guys, if some linear combination of these guys is a 0 vector, then all the CI's are 0, right? All the CI are 0.
Is that a theorem?
So it's it's a proposition. So proposition is sort of like a theorem, but just not as important. It's like a small theorem. It's different from a lemma. A lemma is like a sort of tool that you use, and it doesn't really have much application elsewhere. But you use it to prove a theorem. I mean, sometimes lemmas are pretty potent, but generally lemmas are just these small things, sort of technical tools. Okay. Think about this for 1 minute. See if you can see why this is true. Right? If you have a linear combination of orthogonal vectors, then yielding the 0 vector, then in fact all the coefficients must be 0. Okay. So you only know one thing, right? That the inner product of pairs of these guys, different elements, are 0. Okay. That's the only fact you have. That's the only thing you can use. So see if you can use that fact to show that if this is equal to 0, then all the coefficients are 0. Okay, talk with somebody nearby if you have some idea. Okay, you have only one fact, right? The vectors are orthogonal to each other.
Like it makes sense.
It's two.
Like 2 vectors.
I mean, I don't think it's put it that way, but that works right. That's a new
Okay, does somebody have an idea?
I have a vague idea.
Somebody have an idea? Abel?
Because if they're orthogonal, it's impossible to represent one base and then your combination of the others.
In Euclidean space, yeah. So like, yeah.
I mean, yeah, that's just an analogy. But like, even for orthogonal abstract vectors, it would be impossible.
That's what we're showing. That's what we're showing. So let's think, right? Right. So say that summation ci vi equals 0 vector, right? Right. We want to show that each of the coefficients is 0, right? The only thing we know is something about the inner product. So let's use the inner product, right? Consider the inner product of our thing against Vj. Okay? Right? And secretly, we know that that's going to be 0, right? Because the first thing is 0, right? We're taking the inner product of 0 against something, right? So we know that 0 is this. Okay. Now, what happens when we take the inner product of a linear combination of these orthogonal vectors against one of the orthogonal vectors? What's going to happen? 0, yes. But more, yes, but I know you don't mean this 0. You mean 0. It's also going to be 0 in some. There's going to be a lot of zeros somewhere, right? Right. It's not just one 0. There's a lot of zeros that will occur, right? What's going to happen? You see, well, this is going to. Let me sort of break it up. I don't know if this is going to help or not, but C1 V1 plus Cn Vn Vj. I don't know if that helps you see it. Right? What happens when you take the inner product of this against that? Well?
You can break it to many, like C1, V1, the inner product of C1, V1, Vj, and C2, V2,
Exactly.
Vj.
So you say, well, this is going to be C1, V1, Vj, plus, whoops, C2, V1, Vj, plus Cn, Vj. Right? And now we see the multitude of zeros, right, that Abel was predicting. Right? So most of these are 0, but are all of them 0? No. Which one is not 0? Vj. Right? So Vj is, everything else is 0, but one thing gets preserved, right? The jth entry, the jth summit. Right? Okay, but what's Vj? Is Vj equal to 0? No, right? This is non-zero, right? Because remember, we have an orthogonal set. None of these guys is the 0 vector, right? So this is non-zero. This time something non-zero is 0. So that gives you that Cj is equal to 0. Okay. So let me say up here, like, fix any j where j goes between 1 and n. Okay. And you see that Cj is 0. Okay. So that tells you that all of the Cj are 0. Okay, and so you have linear independence. Okay. Any questions? Any questions? Yeah.
Why are all the other ones 0? Sorry.
They're all 0 because remember, unless should be a 2. Sorry. Right? We get V1 against Vj, V2 against Vj, blah, blah, blah. But the set was orthogonal, right? So, right, the only time that, unless the index equals j, we're going to get 0. Okay. Let me write this. It's actually cleaner to write this using the summation notation. Right? So by linearity, right? So by linearity of the inner product, we can pull the sum and the scalar multiplication out. Right? That's what we did here. Right? That's this thing here. Right? And then you see that as I ranges from 1 to n, at some point I is going to be equal to j, but for all other indices you get 0. So this is going to be Cj, Bj, Bj, Bj. Okay, so that's a cleaner way of writing it. Okay. Okay. Okay, everybody, yes, Connor.
I'm a little confused on how we go from VI, VJ to VJ, VJ. Because if isn't the CI going from I to N?
Yeah, so think like this. So VJ is some fixed number, like 5. Okay, pretend that this VJ is 5. Okay, now I is ranging from 1 to n, like from 1 to 100. Okay, so we're going to get C1 V1 V5 plus C2 V2 V5 plus C3 V3 V5. But for V1 against V5 we get 0. For V2 against V5 we get 0. The only time it's not 0 is when we hit 5. Right? When the index I reaches 5, then that's non-zero. But every other product here is going to be 0. Okay. So only that term is going to survive. Okay, so just one remark. So you see that thus any orthogonal set is a basis for its span, right? I mean, any linearly independent set is a basis for its span. So. Okay. Also notice that if the size of Vi is equal to 1 for all I, if we require that everybody in the orthogonal set is norm 1, then you see that we get this inner product over here against Vj actually is just Cj. Right? It's not Cj times the norm squared. The norm squared is 1. Right? So we just pick off the coefficient. Okay. And this is heading towards what we like, right? We want to be able to just pick off the coefficient. Right? We want to be able to pick off the coefficient in the linear combination to get the coordinate vector. Okay. So it's nice if the norms of the vectors are all 1. Because you see this thing here, right? This thing here is the norm of Vj squared. Well, that would just become 1 and vanish. Okay. This last remark leads us to the following definition. If V1 to Vn is orthogonal, and the norms are all equal to 1, then we call the set orthonormal. Okay, orthonormal. It just means orthogonal, and everybody is of norm 1. Okay, So one dumb comment. If V1 through Vn is orthogonal, then V1 over its norm, V2 over its norm, etc., Vn over its norm is orthonormal. And I always abbreviate orthonormal as ON. Okay, so notice that orthonormal means that Vi against Vj is 0, right? Is 0 if I is not equal to j, and 1 if I equals j. Right? That they're orthogonal to each other and that the norms are all 1. Okay. There's a notation called the Moniker delta notation. Moniker delta notation. Moniker delta notation. So people use this thing, delta sub ij, to stand for something that's 1 if I is not equal to j, and I'm sorry, 1 if I equals j, and 0 if I is not equal to j. Okay, so people usually just write this as this as an abbreviation. Okay, it's just an abbreviation because this sort of thing happens a lot in mathematics. So it's just a common notation. Okay. Okay. Everybody all right? Everybody all right? I haven't done too much. Okay. So here's an example of an orthonormal set. So recall that 1 cosine sine blah 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 is an orthogonal set. With respect to the inner product, 1 over pi times the integral of the product. Okay. If I say what's 1 against 1, what's 1 against 1? Well, I would take the integral 1 over pi, the integral of 1 times 1 between negative pi and pi, and I would get, I'm integrating the number 1 between negative pi and pi, and so I get 2 pi. Divide by pi, I get 2. Right? Right? Harder exercise is to see that sine kx against sine kx turns out to be 1. That cosine kx against cosine kx also turns out to be 1 for all k. Okay, so then if we take that 1 and divide by its norm, and everybody else is already norm 1, we get an orthonormal set. just take everybody and divide them by their norms. Right? You've got an orthogonal set, divide everybody by their norms, you get an orthonormal set. Okay. The dumb comment leads to a boring definition. That is a basis that is orthonormal is called, what's it called? An orthonormal basis. An orthonormal, okay, and this is what we've been aiming at. So, so useful properties of orthonormal bases. And I always abbreviate O net B. Okay. So the first thing is what we've already noticed, that if U1 through UN is an orthonormal basis for an inner product space B, and if V is some element in your space, so if V is some linear combination of the UI, then we can pick off the coefficients as we said we could, right? The CI are just going to be, you take the inner product of your vector against the UI. Right, this is what we did before. Right? Abel, what's wrong?
That V vector, is it the, because we have IPS V and we have the vector V there.
Yeah, this is the vector V, right? So you have an orthonormal basis for an inner product space, and you have some vector.
Or some other vector.
Right? So maybe it's clear if I say it like this. Let this thing be an orthonormal basis for some inner product space. If a vector is a linear combination of these guys, then the coefficients can be obtained by taking the inner product of V against the corresponding element of the basis. Okay, and that's what we showed before, right? We did that right over here. Right? As long as the norms are 1, then you can pick off the coefficients by taking the inner product. Right? We did that already. Everybody okay? We did that already. So for example, say that you have a function, and your function is some combination of cosine waves. Okay. So you have a function, your function is some combination of cosines. Okay. Cosines of increasing frequencies. Then we can determine the CK by evaluating the inner product of your function against the corresponding cosine. Right? Because these guys are all orthogonal. In fact, these guys are all orthonormal. Right? So if I want to know how much of a particular wave is in there, then I just say, okay, I'm going to take the inner product of my function against that wave, and that'll give me the coefficient that tells me how much of that wave is in there. Okay. Right. Or actually, I probably didn't need to restrict this to just cosines. Yeah, I should throw in everything. So let me just throw in everything. Sorry. No, okay, forget it. Okay, so let me pretend that's still there. Okay, let me pretend that's still there. Keep it there. Keep it there. Let me just continue on. In fact, so erased part. So in fact, every function in negative pi pi, every continuous function on negative pi pi can in some sense be represented as an infinite linear combination of the constant function and cosines of increasing frequency and sines of increasing frequency. Okay, this is what's called Fourier series. Fourier series. Every function, you have some function, any continuous function, in some sense, that we're not going to say, can be represented as an infinite combination of cosine, sine, and constant, the constant function plus these waves. Okay.
What do you mean by some sense?
I'm not going to explain. Yes.
Does the Fourier series have anything to do with the Fourier transform?
Yes. Yes. So the Fourier transform is the continuous version of Fourier series. Fourier series is like the discrete version, the simple version, and the Fourier transform is the continuous version. Okay. So we can determine the coefficients by evaluating the inner product of f against whatever. So like f against cosine kx will give you the a sub k, right? If you take f against 1 over root 2, that'll give you a naught. Right? The bk are f against sine. Okay, so this is actually an amazing thing. Let me hold on, people are still waiting. Okay, so this is actually an amazing thing. What it says is that you can take an arbitrary continuous function and then you can actually reconstruct that function as a combination of waves. Okay, and you can figure out what waves, because this is an orthonormal set, you can figure out how much of each wave you need to reconstruct it by taking inner products. Okay, so this is actually the beginning of how you digitize sounds or you digitize images. Okay, that is, you say, okay, I've got this music, right? Here I've got this orchestra playing. Right? What I'm going to do is I'm going to chop it up into pieces. I'm not going to take the whole symphony. I'm going to chop it up into like a few second intervals. Okay, and then I'm going to say, well, I know that this thing can be expressed as a linear combination. So what I need to do is figure out the coefficients. So you have your machine take the inner product of your music against the appropriate wave. And you figure out all the coefficients, right? But you can't figure out all of them because there's infinitely many. But you don't care because human beings can only hear up to a certain frequency. So you stop at the frequency beyond which people can't hear, right? You say, okay, and then you get a bunch of numbers, and you put those numbers on a CD, right? In the old days, right? You put your numbers on a CD, and then, right? Those are the numbers on the CD. It's not the analog sound, right? It's a bunch of numbers, right? You can't draw a needle on your CD and get the sound back like with a record, right? It's not an analog storage, right? So, so you put it in the machine, and the machine says, "Oh, I've got all these numbers. These are the numbers telling me how much of the cosine and how much of the sine, how much of these guys I need." I put it all back together, and I reproduce the music, right? And so this is what this is the beginning of digitization, right? This was initially proposed by Fourier in 1798. When he thought of it, nobody believed him. They said, that's crazy. There's no way that every function can be expressed as combinations of just such simple things. Of course, he was proven correct over time. Okay, so so at the time, people rejected it. They all said, this is impossible. This cannot be true. Okay. So, but it's only true in some sense, and that sense actually is kind of subtle. So I don't want to talk about it. I'm always trying to offer a course that explains what that in some sense means, but like nobody wants to take this course. So, you may never find out. Okay. Yeah, my favorite course to teach is one in Fourier analysis, but I've only been able to offer it once.
So you spent the whole semester?
What's that?
You spent the whole semester talking about that?
Well, it turns out that Fourier analysis this idea of breaking something into its pieces, turns out to be a really fruitful way of doing things. And it allows you to solve differential equations. It has applications in number theory. It's got applications in geometry. It's not just one. It's a very flexible tool that it permeates your entire existence now. That you don't see it. It's not just this. Okay. Yeah, it's something amazing. Okay. Let's go on. So. Corollary of the theorem. Okay, so remember the theorem that we can take off the coefficients by taking inner products. Okay, so let's say that we have a basis U1 through UN of V and inner product space. Okay, and say that you have one vector which is summation Ci ui, and you have another vector V, which is summation Ai ui for U and Vi ui for V. Then the inner product of U against V turns out to be what? What do you think?
Sorry, what is V? What is V?
So there's two. You have a basis of V. You have two vectors, U and V. Right. One guy is summation Ai ui. The other guy, one guy has coordinate vector Ai. The other guy has coordinate vector Bi. What do you think, Adam?
AI plus BI?
AI plus BI? Well, not just that. Right? I mean, actually, not that at all. Anybody see what's going to happen? We're going to get the inner product of AIUI against, let me change the index so we don't get confused, BJUJ. As I goes from 1 to n, as j goes from 1 to n. What's going to happen? Montana.
We're going to get A times, so each time it's going to be UI times UI essentially, which will be 1. No.
The UI times UI will be 1.
Right. And then we,
So what are we going to pick off?
AI and BJ.
You're not. So let's see. Let's work it out. We can pull out the summations, and we can pull out the scalar multiples, and we're left with UI uj. Okay. So what happens? Well, that's going to be 0, except when I and j are the same, right? So as I ranges from 1 to n and j ranges from 1 to n, well, occasionally they're going to be identical, right? When they are identical, only when they're identical do we pick off something non-zero, right? So we're going to end up with AIBI as I goes from 1 to n. Now you recognize what that is. AIBI is the dot product of two vectors. Right? It's a dot product of the coordinate vectors of u and v. Right? So notice that this u against v turns out to be the dot product of the coordinate vector of u against the coordinate vector of v. Okay, so the picture, this sort of parallel universe picture again, you have vector space, you have vector, you've got Rn, you've got coordinate vector, you've got coordinate vector, right? You've got inner product, and you've got dot product, right? Inner product and dot product, but these are actually equal. These are not just a correspondence, these are the same number. Okay, that's what this is saying here, right? When you take the inner product of these guys, you get the dot product of the coordinate vectors. Okay, and notice, there's one last thing to notice. If you just take just one vector, suppose you take just one vector, and you take the dot product against itself, I'm sorry, the inner product of the vector against itself, what are you going to get? That's right, you're going to get summation ci squared, right, from I equals 1 to n. Yes?
Just to clarify, so over there, like we said, UI, UJ is like always 1, right?
But it's going to be 0 except when I and j are equal.
But if it's like, well, because I and J are starting at 1 and going to n,
Mhm.
they always be equal.
actual like.
No, these, remember, it goes like this. I starts at 1, j starts at 1 and goes to n. So you got 1, I is 1, j goes from 1 to n. I is 2, j goes from 1 to n.
Oh,
I is 3,
right.
j goes from 1 to n. This is a double sum.
Okay.
It's a double sum.
Yeah.
So occasionally they, once every time, then they're going to agree.
Okay.
Okay, so this last thing is just the same thing as before, right? It says, well, look, what if we take them to be the same, right? If we take u and u against each other, well, we're just going to get summation ai squared, right? We just get summation ai squared. But that tells us that the norm, which is the square root of that, is the summation of ai squared to the 1/2, right? Which is the magnitude, right? It's the magnitude of the coordinate vector. Okay, the magnitude of the coordinate vector in the L2 sense. In a normal Euclidean sense. Okay, that's it for today. Sorry to keep you over. Hey, Monica.
I emailed you my homework on Friday. Do you want me to bring in a hard copy as well?
That'd probably be nice for the grader. It's not necessary, but if you'd like, if you don't mind. it's
Yeah, for
helpful.
sure.
I have a friends who are math majors, larger seniors, so and some of them they keep their teaching card and they're telling like you need to be awesome. That's why you need it. You get your cheat.
So I mean,
That already happens.
I don't really see how you stuff. That's not always